Thank you, Klaus, for the kind introduction and invite me to give the presentation on the anagram. Yeah, it's my great pleasure to introduce my work here. My title a little bit different from the circulated title. It's from sand to stars because I think sand may be more close to the thing of the anagram, which is linked to granular particles. So yeah, um, when we talk about the particle packing, actually it's looks fundamental, but really very um, important topic, I would say, linked to the application also to the granular packing particles. So I present this first picture to show that it's the structure actually serves as a core to connect different parts. So from the fundamental side, the particle packing actually has been served as a very fundamental model for different matter and understand some phase transition, like the disorder, glass state to solid state or liquid state, that people doesn't understand before using this model. And also, it has also been attract many focus in different fields in the fundamental side, like even mathematics. They are keen to understand how to prove that what is the maximum packing density, uh, not only in our space, like 3D space, but also in high space. So you can see I cited one medal is the 2022 Fields model, which is the highest prize in the mathematical field. That medal is actually awarded to a Ukrainian mathematician for her work on the density sphere packing in high dimensions. So you can see lots of fundamental work are really connected to the particle packing structure. And on the other hand, at the right side, you can see the packing structure determines different properties in the process engineering or even in other engineering like the soil mechanics. So we talk about the bulk density, uh, which is related to the mechanical strength, related to transportation properties like permeability and heat conductivity in the reactors like the fluidized bed. So I also listed lots of application areas, and all of them actually have some, you need to, here or there, you need to use some kind of models that consider the structure of the packing, okay, of the granular particles. And more recently is what I put here at the bottom is now people also think about using the particle model to study the behavior of living systems like the birds. So I will have a little bit introduction of our work in this part recently. And actually that's also linked to Nobel Prize in 2021, who give a physicist for his work on describing the frogs, the birds. Okay, that's interesting. Now, how we do this is we use, like Klaus is also expert in this field, we use a numerical model, which is more cost effective than experimental, to obtain those granular packing structures. And this is really a multi-scale problem because from here we can say, although we target in engineering applications, but the packing structure as a scale between the micro scale and the macro scale or the equipment scale is something we need to have the knowledge on the structure at this scale. So we use like the DEM, which is the high fidelity and validated model to obtain the structure. And to obtain this structure by DEM in turn help establish the mesoscale and the interscale models. For example, what I listed here is once we obtain the high fidelity parking structure model, we can use LBM to study the permeability or drag force from the even microscopic scale, subparticle scale. And I talk about how we do it is mainly by DEM, although of course coupled with other numerical models like CFD, LBM, and DEM. What I presented here, of course, is kind of well known by everyone, I think, governed by Newton's equations. But the complexity normally is really how to accurately calculate the interparticle forces, which depends on many things, material property and particle shape. And later we can see how the forces will control the parking structure. And on the other side, when the early days, we developed the DM model and also develop some different force models. We rely on limited experimental data to validate the model. And at that time, parking fraction or parking structure, like the coordination number, is really something we can find at that time. Although nowadays we have more advanced experimental techniques, even we can measure the particle flow in a microscopic way. So after we obtain the structure, we need to analyze the structure. And as I show in the first picture, the structure of parking, we still call it disordered. Like even the physicists, they call it disordered. That means there's no effective way to really describe it. We need to we need to understand the structure from different perspectives. So we need to use different structure descriptors, or we call it structural characterization. And the first one, of course, is just the packing fraction or porosity, which is the volume that the particles occupy, the real volume divided by the space occupied. But this is really a macroscopic parameter, which is, of course, welcome for engineers because this is just one parameter. But to understand it, we need to use other structure descriptors, like I listed some common one used here. We can group it in some, roughly group it in some kinds, categories, like the radial distribution function is the pair analysis. We understand the correlation between two particles. And the neighbor analysis, we consider the nearest neighbor to one particle, and to describe the relationship between them. So we have the coordination number, just the number. We also have the bond or rotational order, which is to check the rotational symmetry of the neighbor particles. And of course, we also have the Voronoi, the Nolli deceleration, and go beyond from the neighbor is a cluster analysis. So we not only consider two particles in neighbor, we also consider maybe the neighbor of their neighbors or beyond one shell of the neighbor. So that is a cluster analysis, and based on that, we have some pattern recognition, really can identify what kind of specific structure when the cluster is showing in this kind of index. So we can see later. And finally, nowadays people are more using the more advanced theoretical things to understand the structure is from the symmetry and the topology. So here is a list of various studies conducted by me and my colleagues. And by the way, here I would like to introduce myself. Actually, it's from Professor Aibin Yu's group. So I have lots of collaborations with Aibin and did a lot of studies in this aspect together with Aibin and also together with our my colleagues from that group, including Professor Shibo Kwang here. So from this table, although not covered all the studies and not covered other one studies, but you can see really the parking structure has been studied in different process. And we sometimes you combine with different structure descriptors to develop the further model for the applications. And I would like just to show several of the structure descriptors here first, and then I will discuss 3 subtopics for a series study. Okay, so firstly, the RDF, it's famous to identify the medium range order for the granular parkings in even back to 1960s. The famous Burners model for the structure model for liquid and glass transition. If we use the RDF, we can identify some special patterns for non-spherical particles if extended from spherical particles, like what we did in the parking of regular polygons. If we check their RDF, we can really find very subtle peaks, different splitting of different peaks that corresponding to the geometric arrangement depends on different shapes. And also for spherical particles, we can see the distribution also have the split second peak, but sometimes because of its non-symmetric shape, so we will have different peaks in the RDF. So this is one of the structure descriptors showing the different parking structure of different particles. And then the other one I would like to show is a coordination number. Coordination number is probably the simplest one for analyzing neighbors. But if we analyze it through a wide range of parkings, when I say wide range, it's the parking fraction, really from very loose parking for very dense parking of the spherical particles. Even from this simple coordination number, we can understand how the local structure transform for one kind of structure, like if it's smaller than the parking fraction is smaller than 0.62, it's really just a triangle. And when it goes to random loose parking jamming point, the tetrahedral, the tetrahedral start to appear. And then when the coordination number average one is reach 6, which is a normal case, we can see the connection of the tetrahedrals. So you can see using different structure descriptors, we can understand the structure change and the local structure, how the local structure affect the whole structure. And another one is a bond or rotational order is when you obtain the neighbor, the neighbor of the particles of a neighbor, you can further analyze how it arrange the space arrangement of those particles and to identify if they are locally form ordered parking structure. And finally is the cluster structure. That's what I introduced previously. Is we not only look at 2 particles in neighbor, we also check their common neighbors. And from there, we can establish a index system. We can put the first index as if they are in contact or not, if they are neighbor or not. The second index is how many common neighbors they share. Like if they share 5 particles as their neighbors, then the second index is 5. And the third index is how many neighbors will be inside their common neighbors, okay? You can think about it. But with this kind of index, we can actually use a topology, local topology connections to identify different structures, like the BCC, HCP, and FCC here. Like the BCC, the BCC is actually not easy to be directly obtained from the bound or rotational order. So with that, we can understand how many kinds of this kind of cluster level structures can exist in the packing of monocyte spheres, and how the change of these different structures can represent some different critical transition packing structure points. So with this is really a comprehensive description of all the disordered structures that we can find from the packing monocyte packing so far. Then if we want to do some pore size and the local space metric properties, we can use a Voronoi analysis, right? So Voronoi can tessellate the space in a unique way, and each particle can really claim its local office with no overlap with other office, and it's in a precise, mathematically precise way. And once the Voronoi tetrahedral for spherical particles, we can obtain the Voronoi tetrahedral, or sorry, polyhedral. Then we can analyze the local space of each particle according to the properties of this polyhedral. If we want to extend the Voronoi to general non-spherical particles, then we may need to consider to use more like numerical ways, because there's no easy way to get a polyhedral from the non-spherical particle enclose its space. Okay, after I introduce a little bit about the structure descriptors, I want to briefly introduce three subtopics. The first one is the microstructure universality in the packing, and second one is a critical structure change under vibration, and third one is the structure of active particles. For the first one, why we need to find the universality. The universe relationship in the packing structure is very helpful for modeling. So if we can use a single parameter like a packing fraction, we can fully characterize the disordered system. That's a huge information compression. We can establish the model to describe other properties like collectivity, transport properties, but can we really do it? So we need some structural analysis first to confirm this point and establish the correlation if they are really universal ones. And because we did a lot of packing systems, and we find the evidence if we compare the two different packing systems that their microstructures really share some universalities. So we can show later. So the goal is simplify the complex particle physics into robust analytic models. So firstly, this is a kind of hypothesis. So universality. Packing fraction alone can be used to characterize the microstructure parameters for different packing systems, like the packing of wet particles, packing of cohesive particles, packing liquids. And it is tested in the DM simulated monocyte sphere packings and different conditions, covering a wide range of packing fraction range. And then we compare the different structure parameter descriptors. And from these two figures on the right side, you can see we select the packings from cohesive particles and from the packing settling under the in liquid. But if the two particles, even their size could be different, if they the two packings have the close packing fraction, their coordination number distribution is very close. and this figure shows the RDF is also very close. And then we tested other parameters, and we generally find they are close. So based on that, we connect all this data and formulated some general correlations. So we understand because the packing system is essentially a disordered system. So we normally have its distribution and the mean value for all those particle-based parameters, like the coordination number, like the Voronoi tetrahedral metric properties or topological properties. All those properties for its mean and the distribution standard deviation can all be correlated to packing fraction in universal equations. So I didn't list those equations and didn't include all the parameters, but this is really general, and you can find from the papers the detail of the equations. So that's really proved the hypothesis and provide the microstructure universalities that can be used for analytic model. And another universality existed between the force ratio and the packing fraction. So no matter what kind of packing systems is controlled by the force, but there are lots of forces. But then we can use one force ratio that is similar to the bond number, but actually this force ratio also included other modeling like the impactive force and the effective gravity force. Like when the particles are settling in liquid, you have the buoyancy to count some to decrease its effective gravity. But anyway, and even in the electrostatic field, when we see the packing, it's actually not driven by gravity, it's driven by the electrostatic forces. So once we divide the force into several categories, one is the packing-driven force, main force, one is the cohesive force, and maybe another is the process-dependent force, and we put them together to formulate a force ratio. We can also get a general correlation between the force ratio and the packing fraction. So this universality, on the other hand, compresses the information with different DM parameters, right? We don't need those different parameters. We just understand one force ratio, then we can predict the packing fraction. And there are some extension. Those packings are what I call is for sand. So in the engineering particle range. Then if we look at the nanoparticles, which are put in the original title, nanoparticles, we just extend to nanoparticles. And what we find is the universality between the force and the packing fraction can still hold. So this range is derived from the sand, and this one is go beyond to the nanoparticles. But because the nanoparticles, they form some fractal structure, so yeah, we not successfully fully extend the universality, the microstructure universality to the nanoscale, particle scale. But on the other hand, if we go to large particles, and for the universe, we can connect all the stars coordinates, and then we think the structure can be regarded as the packing of these particles in a very loose way. So we can use what we applied in the analysis of packing of sands. We use the Voronoi to tessellate their local space, and then we analyze the local space of each star. And interestingly, what we find is here. So if you look at this figure, this is number of phases for the for the star or for the particles. So only this one is the stars. So only this curve is the distribution of the number of phases per Bernoulli cell. And these ones are the packing of sand of different packing fractions. So if I don't tell you they have different data, one is from stars and the other is from the sand, you may say that looks like the same system. Yeah. So if we check other parameters like the mean value and the standard deviation of the different Bernoulli properties, we can also get very consistent trend for starting from the sand to the stars. Okay, so that's a very interesting consistency, I would say, connecting the structure of our universe in terms of the star distribution and the packing of sand that we can really find on the Earth. And yeah, so that is a hint that maybe there are some hidden common laws in the structure of our system that can be applied across different scales. And the microstructure universality we find can also be extended to multi-size spheres. So we also did a lot of different multi-size sphere packings. And what we can find is their mean value, the partial mean value, which means if in multi-size packing, we have a component with a specific particle size, and we extract all these particles and do the analysis of their properties, then their properties, like the mean value and the standard deviation, can be correlated to their mean packing fraction, which is obtained from their Bernoulli mean value. Okay, that's another extension. And that one can also be extended to the packing of non-spherical particles like the cylinders and the ellipsoid particles. So their Bernoulli cell volume and surface area can be linked to packing fraction also, and their sphericity. So that's a successful extension of the microstructure universality we found in the monosize sphere packings. And when we check the 2D polygons, we can find the distribution have the similar form, but maybe it cannot be simply linked with the packing fraction. And that, from our observation, is actually comes from some local order structure, which is more easily to see in the 2D packings. Then that comes to our second topic. Before that, I will do a summary of the first topic, is that disorder is not randomness. That means we can still find some hidden rules, help us to model the disorder structure. And importantly, if we can achieve the compression of information by using the packing fraction to predict those other microstructure parameters that can help us to establish the analytical models. But we can see if the structure really goes for a critical change, then those laws we may need to consider the different phases where we will have different correlations. And as I previously mentioned, we connect lots of packings, and we identified several packing critical states, identified their structure change, critical structure change points. And one particular critical change is that when the packing goes beyond, the packing fraction goes beyond 0.64, it will have to crystallize, change to the ordered packing. So there are 2 points for the packing fraction with the order fraction. The order fraction means how much percentage. You can simply think it means how much percentage of the packing is ordered. So there are 2 points. The 1 point is the theoretic crystal packing or corresponding to the highest packing fraction. So that's really a a conjecture that have long history back to 17th theory, but just got proved in 2017. And people understand this one can be proved that this is really the highest packing fraction, which is also the most ordered packing. But here is the random close packing point, which is a glass transition point. So although the structure model has been linked with the glass transition, people still do not understand why we need such critical change, why the normal packing will just stop here, will not goes up to here. So in a previous study, we achieved to use the batch feeding and the batch vibration to really achieve to transform the random packing into the ordered packing in this way and reach almost like the highest packing fraction of 0.74. And the structure using the average CN and the Q6 also showed the critical structure change. So at that time, we think we can only use the batch model to achieve the layer by layer ordered packing or the transition from disordered packing to ordered packing. Then the follow-up study, we carefully checked the parameter space, and we understand we can also use a continuous vibration to turn the whole disordered packing into an ordered packing. Maybe not fully ordered, but we can see it will grow. It will grow from the bottom to up. And then we find that if we introduce different vibration model on different containers, we can observe the different ordered packing clusters actually grows from different boundary. So we have boundary effect, and we have something similar to the crystallization nucleation theory, that the crystal start from nucleation and then grows with time. And more interestingly is that once we understand why we can obtain ordered packing clusters from different geometry, but finally they cannot form perfect ordered packing, is because of the conflicts of these crystals. Because crystals, they have certain orientations. So they will have conflicts in their orientation that between different ordered clusters. But once we can carefully design the geometry shape, the container shape, to eliminate these possible conflicts, what can happen is that we can design some container that really overturn our understanding. The previous understanding is the particles will always form disordered structure. But if we can carefully design the boundary to eliminate the symmetry breaking, then we can obtain the ordered packing without vibration. So that's really interesting and almost like close this question from what I think. So we also tried using our, although that is a very specific case, we also try to use our understanding on the effect of vibration on the particle structure change. Even in the vibrated bed, we have the percolation, we have the segregation. We find that vibration amplitude vibration velocity amplitude is a better parameter to characterize those dynamic behavior. That's what we have learned from when we do the self-assembly. But as I noted here, so a theoretical model is always good, but always it is very difficult to obtain sometimes, and AI knows it. So it's just a small example that if we forget about, we really want a theoretical model, we just use a data model. We may also, nowadays, because AI is so powerful, we may also directly obtain some close-up functions that including different particle size. So we ignore their structure, we directly derive the effect of different particle size, different particle properties on their dynamic behaviors. Like in screening, we can obtain its screening performance with the AI to close up the missing governing equations. So anyway, but that's two approaches. One is really from theoretical, one is just using data model, but maybe they can be combined, like what we did here. Some difficult part we can use AI to close up. Some part we can just use some simple theoretic, like the continuity to form the whole process model. Okay, this is my summary of subtopic 2. So basically, self-assembly or order transition is a very interesting phenomenon in the packing. It will also affect the analytical model, and it's really more maybe can be linked to more fundamental things like the symmetry design than what we think. But anyway, that brings another question: is there any other similar order or symmetry in the particle system? So that's my final topic. I will just briefly introduce it. Is the recent very interesting topic is active particles. So when we talk about active particles, it's a connection of individuals that are capable of self-proportion and widely used in model the connected behavior of systems. So I put a beautiful picture here is because it's really connected with the active particles or the active living systems. So how the birds fly in a very beautiful pattern, like even the famous poem in the Chinese describe these beautiful pictures is because of the very, you can see a law. You probably can see a natural law from the bird when they are flying. So actually, people already did this kind of physical model on this kind of frogs, which is called the active particles. So these particles, they can understand what happens on their neighbors and adjust their flying direction, trying to align it with their neighbors. And with just that kind of rule, the whole system can achieve a global order. That means they can move in the same direction to resist the noise. So the first pioneer work is called the Vischek model, which is still used nowadays. And with that model, the Professor Thomas Vischek won the 2020 Onsago Prize. And following his study, there are lots of related studies. And one is I already mentioned is about the 2023 prize is for Professor Parasi. One of his work is studied the real frogs. And he proved that really why these frogs fly in this pattern is because there may be a simple alignment rule between their neighbors. And there are other related studies, even the alignment rule is considered in the voter model. That means if you vote someone, who will affect you? Maybe it's your neighbors. So one example is that someone guess who will win in the US election. They don't ask themselves. They don't ask who will vote. They ask the neighbors. And from the neighbors, they derive a model and successfully predicted who win the election. And our recent studies try to apply the structural analysis to this particle system. So we use the network analysis. So not only the neighbors, but also the clusters to describe the Vischeck system. And very interestingly, we found that with a structure descriptor of the average connector, we can uniformly correlate the structure with the order parameter, which is how uniform all these particles will fly into one direction. And we also find the very similar to the microstructure universality. We also find some structure universality or self-similarity in different scales in the Vischeck system, including the cluster level and the global level. The distribution of the connectivity shares the same normal distribution pattern. And using this, we also see that the cluster's orientation can be characterized with its size in a universal way. With that, we can predict the system's behavior. Here is the global order from its structure. So it also proves in another particle system, active particle system, the structure has the laws. And if you understand this law, you can derive the system's performance based on these laws. So maybe there will be a good comparison between active particles and granular particles. I listed some, put some question marks, which can be inspired from the granular particles. And this is my final slide, is to summarize the third subtopic. Granular particles and active particles are typical models for the non-living and living systems. But from the both systems, we can see there are structural universalities which can be used to model their behavior. So like what Evan Schrodinger did in his last period of research life is to find what is life. So probably I very broadly ask this question: can we use the structure and the connective behaviors relationship to break this gap? That means the boundary between the non-living and the living systems. So with that, I call my group as odds, which is the order from disorder. And thanks for all my PhD students, and particularly for Reggie, Jiga, and Ango Bu, who contributed in today's presentation. Thank you. That's all. Any questions?
Thank you. Thanks, Kejun. Excellent presentation. Much appreciated. Yeah, we can open the floor now for questions. I'm sure there are many questions out there, so feel free to unmute yourself and just speak up, or you can also just place the question in the chat, but we would prefer to have you sort of speak out. We are a small community, so yeah, feel free to sort of speak out. Any questions? Anyone wants to start off? If not, I might just quickly kick off. So I really enjoyed your presentation, Kejun. And one thing that popped into my mind is the question about universality, right? You started off with spheres, and then at the end, you kind of briefly talked about non-spherical particles. And I guess that's a very challenging terrain because universality applied to any sort of particle shape is really challenging. You showed some examples where you still have ellipsoids, cylinders, so you have some symmetry, some simplifications in there. But I guess once we're talking arbitrarily shaped particles, it's going to be very difficult. Can you just comment on that?
Yeah, that's a very good question. Yeah. Um, I couldn't say we can have a general correlation for all shaped particles, but from my observation, if the particle is not extremely prolonged or thin, if it hold a kind of um, isotropic, a kind of isotropic, but not that isotropic, then to some extent, I think the general universality can still be held. But if it's really very, very like it's not the 3D shape, it's almost like a 2D shape, then the law should be revised. Yeah.
Mhm. Thank you. And just another comment sort of you made in terms of, from sand to compare sand with stars or, even the nanoparticles to stars. And now sort of your last topic where you talk about active particles. I found that really interesting. And I mean, people are using those concepts. Yeah, you mentioned for birds, that they use it for traffic modeling or, some
Exactly.
sort of
Yeah.
maybe people. Um, I guess there is a very broad application on some concepts that we apply. And I just maybe, if you just comment on where do you see this going? Do you think that using particles we can pretty much describe everything?
Yeah, maybe I'm not uh my knowledge may be not high enough to answer this really very important and fundamental question. But to be frank, I'm always thinking it's actually related to our fundamental problem is that how do we interpret our world? Is in a continuous way or a discrete way? So we can see maybe sometimes we need this discrete way, sometimes we need to use continuous way, but from the when we link them, they are always they are always something that related to the structure of the discrete particles or discrete elements. So only by solving the structure can we link the discrete scale to the continuous scale. Yeah.
Yeah, no, that's a really good answer. Um, any other questions?
Hi, Kejun.
Yeah,
Yeah, it's
super.
very nice presentation. So very interesting to see you try to change the geometry to get ordered parking. I just wonder, have you tried, say now you change the whole geometry, if from engineering application, we just control the geometry at the feeding system, then probably we can get a dense parking for applications. Is that possible?
Yes, that's really possible. That's a very good question. Although I myself I haven't followed up my that study, but I can give you some examples. One example is actually before us, there is a patent in US that they try to design a shape to help the colloid particles to form crystal structure. That for colloid particles really is just to use the container shape. And then I also find recently there are studies in vibration, in design the vibration and the geometry of the hopper, like what you said, to get a dense layer, to get the dense structure when you layer the 3D printing particle layer. They are also trying to do that.
Okay,
And
gotcha.
and in physical society, there are some studies using the confined geometry to help self-assembly of ellipsoid particles. That I can also see. Yeah.
Thanks a lot.
Any other questions, colleagues? No more questions? Still have time for a few.
Yeah, I may use the more time than I expected because Klaus, you said up to 40 minutes, but when I check, I used the 45 minutes. Yeah.
That's fine. Usually, as I said, we have a discussion at the end, and we try to stick to 15 or in total, sort of to an hour. But yeah, it just depends how everything evolves. Well, I have another sort of question, or I mean, you mentioned DM is, readily used for these sort of things. Is the data that you showed, or most of the data, derived from numerical simulations, or is there also some experiments, or are the experiments mainly used to calibrate the models?
Most of them are from simulations, but the model before we run the simulation are calibrated by different experiments. Yeah.
Yeah, okay.
Yeah. So I think nowadays we can trust DM in most of the predicted particle systems with very good calibration. Although how to calibrate is still an open question. Yeah.
Yes,
yeah.
yes, I agree. All right, colleagues, any other questions, comments?
Yeah, welcome your comments offline by sending me an email. Yeah.
Yeah, thanks for offering that, Kejun. Definitely stay in touch and hopefully see you again at some of our other events. Well, if there are no further questions, let's thank Kejun again. Thank you so much for making yourself available for this webinar. As I mentioned at the beginning, the webinar is recorded and we're going to upload it on our YouTube sites. Also, as I mentioned at the beginning, we have a LinkedIn site where we announced our new logo and everything. So we will also sort of write a post there to make sure that people are aware that this is available, this recording. And I would also recommend you to keep an eye on our LinkedIn site. We will still aiming to send out newsletter maybe every quarter, but we will definitely be more sort of announcements on LinkedIn.